Sir. Hello.
Yeah, so this is Sai Dinesh. I'm a PMRF TA for this NPTEL course E2004 Digital Signal Processing. Um, so, welcome to week 3 and week 4. So, I'll be covering topics from week 3 and 4 in this lecture, partially from week 3. So, just okay. So first I'll talk about. So, in this lecture, I'll first talk about LCCDA systems. Sorry, systems governed by LCCD equations. Systems with LCCD equations. That is part from week 3, and then I'll go to week 4, which is the uh, Z transform. Right. So first I'll just talk briefly about LCCD equations. So yeah. So there these are a type of class of systems. Uh, so LCCD is known as linear constant coefficient differential for the continuous time, or difference for the discrete time equations. So we're talking about a class of systems where which are for which the input and output are related through a linear constant coefficient differential or difference equations, right? And then, like, for the continuous time, it is the differential, they are governed by the differential equations, and for the discrete time they are governed by the difference equations, right? So first we'll just talk about continuous time for a while. So for a continuous time, um, like a general nth order system, or general nth order system is k equal to 0 to n a power k, k by dt power k. Is the kth derivative, and then k equal to 0 to m bk dk x of t by dt per k. So this is a nth order system. Nth order system that we have here. So this, if you see, it's like a in the form of a differential equation. So these are known as, and these are constants actually. So this is why it's known as linear constant coefficient differential equations, right? So this gives actually they describe a implicit specification of the system, that is, they describe a relationship between input and output rather than explicit expression for the system. And then, in order to get the explicit expression, that is the relation between the input and output, we need to solve this differential equation. We need to solve it, right? So a differential equation just by in itself does not give a solution. uh, we need some more, and those are known as the auxiliary conditions. So to solve a to get a solution, we must specify a equation. We must specify one or more auxiliary conditions, and then in our case we'll be talking about LTI and causal systems. So these have a particular type of auxiliary conditions. Have a particular type of auxiliary condition known as the initial rest, right? And known as the initial rest. So like different auxiliary conditions lead to different solutions for the system. So like this describes, so a differential equation just describes a constraint between the input and output of system, but to characterize the system completely we must specify the auxiliary conditions as well. So different choices, different auxiliary conditions lead to different systems, right? So let's just take an example in the continuous time. Let's just take this is an example from the textbook. So let's say we have a system governed by this k into e power 3t into u of t, which is a, uh, a differential equation, right? So usually the sorry, this is the input, okay, and the differential equation is dy of t by dt plus 2 times y of t is equal to xt. This is the LCCD of the system, right? And this is the type of the input that we have, right? So usually the output is actually a sum of a particular solution and then a homogeneous solution. So homogeneous solution is y of t is the output when the input equal to 0. So this is the homogeneous solution. These are also known as the natural response of a system, also known as natural response of a system, right? So this is the yh of t. So even when there is no input, there is a particular output. That is, for 0 input there is a particular output, and that is known as the homogeneous solution. And for the particular type of input that we give, we get an output that is called the particular solution, and the final solution is the sum of particular and homogeneous solutions, right? So a common particular solution is when let's say in this case what we first hypothesize is we start from a forced response that is they are the same form as the input, which have the same form as the input, right? So let's say yp of t is y times e power 3t. When input is k times e power 3t, we are taking y times e power 3t as the input. So if you put it in the equation, in the differential equation that we have 3y e power 3t 2y e power 3t is equal to k e power 3t, which implies k is equal to 5y, or y is equal to k by 5. Therefore the particular solution is k by 5 e power 3t. So this is the particular solution, right? So now we talk about the so this is the first part. Next is the homogeneous solution. Homogeneous solution is when the input is 0, right? So 2 y of t plus 2 of yt equal to 0. Sorry, 2 dy by dt equal to 0. So let's take yh of t in the form a into e power st. So in that case, if you put it, we get a s e power st plus 2a e power st is equal to a into e power st into s plus 2 equal to 0, which implies s equal to minus 2. Therefore, we have y of t is equal to a e power minus 2t plus k by 5 e power 3t for t greater than 0. So this is the type of the solution that we have. But here, this is not fixed. So here we have not characterized the value of a. So we have not characterized the value of a, and giving different type of auxiliary conditions, we get different types of a, and then we get different types of systems here, right? So these are this fixed auxiliary conditions, right? So for our case, we are considering LTI and causal systems. So for LTI causal systems, the auxiliary condition that we take is the initial rest condition. The initial rest condition means that if input x of t equal to 0 for t less than 0, the output y of t is also equal to 0 for t less than 0. This is known as the initial rest condition. Like, this is for the causal part, but usually we can say that if x of t equal to 0 for t less than t naught, then y of t equal to 0 for t less than t naught. So that is another form of the initial condition have here, right? So if we take y of t equal to 0 for t less than 0, then what we have here is 0 is equal to a plus k by 5, which implies a equal to minus k by 5. Therefore, for t greater than 0, y of t is k by 5 times e power 3t minus e power minus 2t. So this is the system, which is LTI and causal. Okay, so this is the system that we have for LTI and causal. So basically we have a system of this form, but this is just a constraint. Once we fix the auxiliary conditions, like we have the initial rest condition here, then we get the LTI and causal system governed by that LCCDA. So this is for the continuous time. Similarly, we have a discrete time as well. And then an nth order system is governed by k equal to 0 to n ak y of n minus k is equal to k equal to 0 to m bk x of n minus k. If so, now we have two types of systems. So if we find the h of k, which is the impulse response, they are of two type, which are infinite impulse response and then finite impulse response. If for an IIR system, at least one of the AKs are non-zero. If all AKs are equal to 0, then it is an FIR system. So these are the FIR and the IIR systems that we have. So if we see, this actually can be written as yfn is equal to 1 by a naught, k equal to 0 to m, bk x of n minus k equal to 1 to n, ak y of n minus k. This is in the form of the nth order system. So this is known as the recursive equation, basically. Why? Because we see that y of n is dependent on the all the previous solutions and the previous the input at a previous time instant. So this is known as recursive equation, right? So infinite and finite impulse response. So let's just take another example from the textbook, which is y of n minus half of y of n minus 1 is equal to x of n. Again, even in the discrete case, we have both homogeneous solution and a particular solution. So let's just take the input as x of n is equal to k times delta of n, initial rest with the initial rest condition. Right? So in this case, y of 0 is equal to x of 0 plus half y of minus 1, which is equal to k. So if we continue this, y of 1 is equal to x of 1 plus half y of 0, which is half k, and then y of 2 is x of 2 plus half y of 1, which will give to 1 is equal to x of n. So yn minus 1 equal to 1 by 2 power k. So we are doing it in a recursive manner, right? So if we see, we get the impulse response of the system h of n to be 1 by 2 power n into u of n, right? So now if we see, this is an infinite duration signal. This has infinite duration, basically. So this is an IIR system. Right? So this is something about the LCCD equations. So any doubts until here, until the LCCD part? Hello? Hello? Akhil, are you there? Hello. So let's take let's just do an example. Alright, let's take example to see if what are which of them are FIR systems. So let's take the first one, which is yfn is equal to 2fx of n plus 3fx minus 2. Is this an FIR or an IRS system? Okay, so if we write it in the nth order case, in the nth order form, we see that all the a case are 0, right? So this is an FIR system. Let's take another example where yfn is equal to 3 times yfn minus 1 plus x of n minus 1, right? So here we see that a1 ak equal to 3 for k equal to 1. This is an but there are also recursive forms. So check them. I'll just be giving hints, right? And this is how you should go about answering the solutions here, right? So let's just, so if everything's clear, we'll just move on to the week 2 syllabus, which is the week 4, sorry. So here we'll talk about the z transform. So the z transform x of z of a sequence x of n is given by x of z is equal to minus infinity to infinity x of n z power minus n, and this like notation is this is the notation. we have. So in the context of LTI systems, if we have x of n passing through a system with impulse response h of n, and we get y of n at the output, y of n is equal to x of n convolved with h of n, which is equal to h of k x of n minus k. Okay, so minus infinity to infinity. But let's consider a signal of the form x of n is equal to some z naught power n, which implies y of n is equal to k equal to minus infinity to infinity h of k z naught power n minus k, which implies z naught power n k equal to minus infinity to infinity h of k z power minus k. So if the input is z naught power n, the output is also z naught power n by some constant value. So this is known as the, so if the input, so it's like ax equal to some lambda x. So this is of the form ax equal to lambda x, which implies x is the eigenvector, and then lambda is the eigenvalue. Therefore we write y of n is equal to z naught power n into h of z for when y of n passes through h of n to get y of n, sorry, x of n passes through h of n to get y of n. So here this is known as the eigen signal of the discrete time signal. So finally, what have we discussed? hf for any signal for x of n, x of z is equal to n equal to minus infinity to infinity x of n z power minus n. So if we let's say we have x of n to be 0 0 1 2 3 again, and then 0 0 0, and this is for n equal to 0. So for this, the x of z will be t, which is equal to 1 into z power minus 1 plus 2 into z power minus 2 plus 3 into z power minus 3 plus 0 0. Therefore x of z is z inverse plus 2 z power minus 2 plus 3 z power minus 3. Which is the z transform. Right. So one more important example is, let's say x of n is a power n into u of n. So in this case, x of z is equal to n equal to minus infinity to infinity a power n u of n z power minus n. So because of this u power n term, we get n equal to 0 to infinity a power n z power minus n, 0 to infinity a z inverse whole power n, which is equal to 1 by 1 minus a z inverse. This converges provided mod z less than mod a. So basically mod a z inverse less than 1, which implies mod A is less than mod C. This is clear. So along the same lines, let's say we have another example. X of n is minus a power n u of minus n minus 1. So this has support minus infinity to minus 1. So we write x of z is equal to n equal to minus infinity to infinity a power n u of minus n minus 1 z power minus n, and upon solving we get 1 by a z inverse again, but here we need mod z less than mod a. So this is where it will converge. So these are known as ROC, which are known as the region of convergence. So Z transform is always accompanied by a RAC. ROC, right? So yeah, let's move on to the, with this knowledge, maybe we can move on to the, I'll open up the assignment and then we'll give you some hints along the way. Alright, so so first question is, if y of n is equal to x of n convolved with h of n, then sorry, this is sorry, I am so let x of c be the z transform of x of n, that is x of n and x of z be a z transform pair where z naught belongs to c, right? Then x of z naught, so z naught belongs to complex field, complex numbers. So then is x of z naught guaranteed to be finite, to be a finite quantity? Is that so? So let's see. So what do we have here? X of z is equal to minus infinity to infinity x of n into z power minus n. So z belongs to c, right? So z naught belongs to c. Let z naught is equal to r e power j omega naught in the Euler's form. So in that case, what will x of z naught be? X of z naught will be n equal to minus infinity to infinity x of n r e power j omega naught power n, sorry, minus n, right? The modulus of this is equal to modulus of this but then the modulus of the e power j omega naught term is equal to 1. So what we are left with is the modulus of mod x of n into r power minus n. Is this finite? This is what you need to find. So when will this converge, and does this converge? Does it always converge? This is what you need to find. Okay, so let's see question 2. Let x of n convolve with and x of z is again a pair where x of n is finite duration. So what is the ROC of this? This is what is the question is, right? So what is x of z? Again, let's just write the formula. X of n is equal to minus infinity to infinity x of n z per minus n. So this is finite duration. So if x of z is finite duration, implies x of 0 not equal to, I mean, can be non-zero for both n less than 0 and n greater than 0, right? So in that case we will have many z terms, so we will have the corresponding z terms, right? So if we have a z term in the Fourier equation, will there be a pole, or if we have a z inverse term, will there be, right? So that is what you need to find, like what are the points which are if which are included in the ROC, they do not converge. So if they should not, the ROC does not contain the points for which the z transform does not converge. So that is what we need to find here in this question, in question 2. See question 3. So question 3, so now is the algebraic expression of x of z is sufficient to determine the corresponding time domain sequence. So we have x of z, does it imply we have x of n? So take an example. As we did earlier, a power n u of n into a power u of n minus 1. Find z transform and see if they are same or different. So now question so question 4 is hello, Akhil, are you there? Hello Akhil, are you there? let's move on. Let's now given, so now here we do not know the ROC, so we cannot so but then what if we know the ROC? What if we know that the signal is left-handed or right-handed? Can we then find the original sequence? Sorry, I mean, can, if we know that it is left-handed sequence, but then we only know that it is x of z, is x of n unique? Once you get the question 3, I think this should be clear, right? So if you have an x of z, when there are only few possible ROCs, like for example you have a x of z and then you have a particular system of poles and zeros. In that case you only have a very few options available for the ROCs, and then you have to see among which ROCs is the properties of the x of n, for which ROCs are the properties of x of n followed. So that is what you need to find in question 3. And another example, let's go to question 4. So let's say if x of n belongs to real value, then is x, does this happen whenever z belongs to real value? Any idea how to so what do we have? We have x of z is equal to x of n z per minus n, but we know that z belongs to a real value. That is what the question is. So if whenever there is a z, let there is a z naught which is real, so in that case x of z at z naught is x of n into z naught power minus n. Hello. Hello.
సార్ అది క్లిక్ అయిపోయింది సార్.
Hello, Akhil, are you there?
Yes sir, yes sir.
Okay. So we have x of z for z equal to z naught, so z naught power n, but then if x of n is real, is this real? Need to find out. So basically for all the questions what we're doing is just writing out, expanding it in the form of a z transform and putting whatever conditions are available in the question, then validate what it turns out to be, right? So the fifth question, if ROC of x of z is of the form the form 0 less than r1 r1 less than mod z less than r2, so this is the ROC form where 0 less than r1 less than r2 less than infinity. Then x of n can possibly be a two-sided finite duration sequence. So what he's saying is this is the ROC that we have. He's saying that there is an R1, then there is an R2, right? So we have one R1 and we have R2, and he's saying that this mod z is in between R1 and R2. So let's say this is the area. This is the area that we have. R1 less than mod z less than R2. So can this be a two-sided finite duration sequence? So we know that for the examples that we have done, like for example a power u of n and a power u of minus n minus 1, this is a right sided sequence and this is a left sided sequence, and we have seen that ROC for so like right sided sequence will have ROC which lies outside a circle with some radius. Yes, and then we have a left side a sequence for which the ROC lies inside a circle, basically. So here we have a common area in between two circles R1 and R2, and then the ROC is between them. And then whenever we have a sequence, let's say like some x tilde of n, which is x1 summation of x1 tilde of n and x2 tilde of n, we find the ROC of 1 and then ROC of the signal 2, and then we find the common region. So what do you think is the intuition from having an ROC in between the two circles? Can anyone answer? Okay, so here we have here in the case of having a summation of two signals, we find ROC1, and then sorry, let's just write it. We have ROC1 and ROC2, and then we find the common region. So this from this intuition we need to find it if it is a double-sided sequence. Okay, any questions until now? Someone has joined, or do you have any doubts in the assignment or in the concepts from Z transform? Hello, is anyone there? Okay, so I'll go ahead with the assignment questions. So we have a system transfer function with 3 z cube plus 1.75 z square minus z plus 1.33 by z cube. So is this an IR or an FIR filter? FIR or IIR? We need to find it. So here we see that the numerator order equal to 3 and then the denominator order equal to 3. So if we divide the z cube, what we have is 3 plus 1.75 z inverse minus z power minus 2 plus 1.33 z power minus 3. This is what we have. So basically we have three zeros and 3 poles. So this is the system function that we have. Is this an or FIR or IIR? To get this, do AZT. This is intuitive. Okay, so this is what we need to find. Is it an IAR or an FIR filter? Okay, any questions? Want someone, can someone answer for me, please?
So after finding inverse Z transform, how we can decide it is an IR or FIR, sir?
Yeah, so basically, if so once you find the inverse Z transform, what you get is a H of n, right? So if the H of n, if the duration of H of n is infinite, then it is an IAR filter, and if the duration of H of n is finite, then it is an FIR filter.
Okay, sir. Thank you.
Yeah. So any problem in the previous questions? The double-sidedness, real parts, third, second, first questions, or any concept doubts that you have in regarding Z transform? Anything?
No, sir. No, sir.
Sorry.
No, sir. You can continue, sir. No problem.
Okay. Yeah. Okay. So let's move on to the seventh question. So he's saying in the assignment it says x of n is equal to 0.5 power n u of n minus 2 by 3 power n u of minus n minus 1. Okay, so this is the question, and we need to find the x of z and ROC, right? So split it up into two parts. We have x1 of n and then x2 of n. So we have x1 of n is equal to 0.5 power n into u of n. So how do we find this? Equal to minus infinity to infinity x of n z power minus n, right? So this is equal to n equal to my, since because of the u of n term, 0 to infinity 0.5 power n z power minus n, and then you solve it, find the ROC 1. And similarly you take x2 of n, which is minus 2 by 3 power n u of minus n minus 1. So again do the same thing, which is minus of n equal to minus infinity to minus 1, 2 by 3 power n. Do the change of variables, and solve for x2 of z and ROC2. So yes, so what I was discussing was, we have a signal x of n, which is a summation of two signals, 0.5 power n u of n and then minus 2 by 3 power n u of minus n minus 1. What we're trying to find is the final x of z for this x of n and the ROC. So what we're doing here is splitting up the signal into two parts for x1 of n and x2 of n, where x1 of n is 0.5 power n into u of n. Earlier we have seen how to do the Z transform for this type of signals. So apply whatever is there here for this one and this one, find x1 and x2. So final x of z is equal to x1 of z plus x2 of z, and then ROC of x of z is ROC1 intersection with ROC2. So this is how you get the final x of z for this signal. So yes, so this is the signal. This is the seventh question of the assignment. Now let's go to the eighth part. So eighth question, any doubt until this point? Someone new has joined. Do you have any doubts in the assignment questions or in the concepts of Z transform?
No, sir.
Okay. Okay, let's just do the eighth problem. Okay, so let x of n is equal to 2 pi power n u of n minus 2 power e power 2n e power j3n e of minus n minus 1, and we need to find the value of z naught for which x of z naught equal to 0. Okay, so x of z naught equal to 0 means that it is a 0 for the system. It is a 0 of the system. So what we need to do is find x of z. We need to find x of z. That is the z transform of x of z, right? So how do we do this is find x of z and then find the zeros and poles of x of z, and find the zeros of x of z basically, right? So solution would be find x of z and then put x of z in the format of p of z by q of z, where this is numerator and denominator. Solve for p of z, we get zeros for the system. If z naught is a 0 of the system, which implies x of z naught equal to 0. So this is what you basically need to do. So again here also we can split up the signal x of n. X1 of n is 2 pi power n into u of n, and then x2 of n is minus e power 2n e power j3n u of minus n minus 1. Find x1 of z and ROC1. Find x2 of z and ROC2, right, and then add them up. So if you want to see that x1 of z is equal to n equal to 0 to infinity 2 pi power n into z power minus n, which is equal to 2 into sigma n equal to 0 to infinity pi z inverse power n. Solve it, and then x of this one would be n equal to 0 to infinity e power minus 2n e power minus j3n z power minus n, which implies e power minus 2 e power 3j into z power minus 1 whole power n, from n equal to minus infinity to minus 1. Here upon solving we get x1 of z and x2 of z, and then for the values for which they converge we get the ROC1 and ROC2, and final ROC is ROC1 convolved with intersection of ROC1 and ROC2, and final x of z is x1 of z plus x2 of z. This is the 8th question. Any doubts in 8th question?
No, sir.
Okay. Yeah. So let's do the 9th question. So I'll be solving sorry. Yes.
Sir.
Yes. Yes.
So he has to find the Z naught, no, sir.
Yeah.
Okay, so we are finding the region of convergence,
Okay.
and you're told that you need to add the x1 of z plus x2 of z.
Okay.
So at last we need to substitute z is equal to 0. What? How to find the value of z naught?
How to find? So basically, once you get x of z here,
Okay.
once you get x of z, you will get it in the in form of denominator by numerator form, right? So if you solve for the numerator, you get the zeros. Like this will be of the form like z per z minus a, z minus b by z minus c into z minus d. If you solve so here a comma b are zeros, right? So in this system x of z, what we need to find are the zeros.
Okay.
So here once you find x of z, put it in this form where p of z by q of z, and then solve for the numerator.
Okay. So only for numerator we need to solve.
Yeah, only for the numerator you need to solve the question.
Okay.
Like you
So
can.
whatever will be the answer, if z equal to 0, we will be having the value of a or b, like that. Huh?
Sorry, can you repeat?
If you are getting substituting z equal to 0, z minus a is equal to 0 means
Yeah, z minus a equal to 0. Yeah, correct. So
and
solution.
z is equal to 0.
Yeah,
You will be getting in that manner.
correct. So like solve for p of z equal to 0, right? So if you solve for p of z, so here p of z is equal to this one. I mean this can also be, I mean you might also get it in the form like 1 minus a z inverse into
Yes,
1
sir.
minus b z inverse. Like you can get it in this format.
Yeah.
So here also it is the same thing.
Okay.
Right, so once you get the numerator, you need to just solve the equation, then you will get the zeros for the system. So that is what is the question. Find the value of z naught for which x of z equal to 0 means that it is the 0 of a system. You need to find the zeros for the system.
Okay, sir. Thank you, sir.
Yeah. Thank you. Any other doubts?
No, sir.
Okay. So question 9, I'll be solving a similar question. I mean, okay, so I'll just write the question in your assignment anyway. So let x of 0 has a, so possess a trivial 0 and then a 0 at, this is the first one, and second one is 0 at z equal to z naught, and at z equal to z naught, right? And two poles at z is equal to p1 and p2, where we have mod p1 greater than mod p2. And then one more thing that he has given us in the question, limit z tends to infinity minus x of z inverse is equal to 1. Okay, and also one more thing that he has given in the question is x of 1 is equal to p1 plus p2 by 2 minus p1 p2 by 1 minus p1 plus p2 plus p1 p2. So once we have this information, and now we need to solve for the I mean we need to solve for the x of n basically, right? So what do we have here? So 0 at Z0 and 0, poles at P1 and P2, right? So how can we write this equation in the form of poles and zeros? We need to write it in this form. How do we write it? Can you help me? This will be Z0 Z inverse, P1 Z inverse, you can write it neatly, 1 minus P1 Z inverse, 1 minus P2 Z inverse, 1 minus Z0 Z inverse. So this is what it is, right? Is this clear? And then 1 minus 0 into Z inverse, which is equal to 0 anyway, 1 anyway. So what we have is x of 1, we have some value. What if we put x of 1 minus Z0 by 1 minus P1 into 1 minus P2? But for this, what he has given, P1 plus P2 by 2 minus P1 P2 by 1 minus P1 plus P2 plus P1 P2. This is what he has told, right? So this numerator and this denominator matching exactly, if you can see. So these numerators are also matching. So we know 1 minus Z0 is P1 plus P2 by 2 minus P1 P2. Therefore Z0 is 1 minus P1 plus P2 by 2 plus P1 P2. Clear? So this is what Z0 is. Okay, and now what he has told us, x of Z inverse tends to for Z tending to infinity becomes 1, right? So sorry, we have x of Z is equal to P1 plus P2 by 2 minus P1 P2. Oh, sorry, let's just write 1 minus Z0 by 1 minus P1 Z inverse, 1 minus P2 Z inverse, Z0 Z inverse. So x of Z inverse will be 1 minus Z0 into Z by 1 minus P1 into Z, 1 minus P2 into Z. Okay, now limit for Z tends to 0, right? So if we divide by Z inverse, what will we get? Z inverse minus Z0, Z inverse minus P1. Sorry, we need to multiply. Then there is one multiply with Z per minus 2. So if you put 1 Z per minus 1 inside, Z per minus 1 minus Z0 into Z inverse by Z inverse minus P1, Z inverse minus P2, right? If Z tends to infinity, what he said, that limit Z tends to infinity, Z inverse minus Z0 into Z inverse by Z inverse minus P1, Z inverse minus P2 equal to 1. So if z tends to infinity, z inverse tends to 0, right? But then if we have, but then we have a z inverse in the numerator. What does this suggest? It means that this z inverse is getting cancelled somewhere, right? So if that z inverse gets cancelled, we what we left with, then this z inverse term would vanish. This z inverse term would vanish simply because if z tends to 0, z inverse tends to 0, but then it is equal to 1, so this is not possible. So this should cancel out. This will cancel out with one of these, and then if we put z tends to 0, we will have minus z naught and then minus p2, which means z naught equal to p2. And then now we have p1, p2, z naught. So we have the x of z. Understood?
So can you please repeat the last step, sir?
So basically, so I mean, I'm not, I should not be solving the entire solution. That is why I told the last step. So basically, what we have is z tends to infinity. He told that z tends to infinity. This whole part is equal to 1, right?
Yes.
But then when z tends to infinity, z inverse is equal to.
0.
But then if this is 0, can this be equal to 1?
No.
So this should cancel out, right? Clear?
Yes, sir.
Yeah. So this should cancel it with one of these. So we know what p1 is. Let's say these two are cancelling out. So we know what p. Sorry.
Okay, sir. Understood.
Yeah. So if these two cancel out, we are only left with this part. If you put z inverse equal to 0, these two are gone. What you are left with is z naught by p2. Correct?
Yes, sir.
Yeah. So z naught by p2 equal to 1, which implies z naught equal to p2. So earlier we got z naught, now we got p1, now we got p2. So we have the x of z. Understood? Is it
Yes.
clear?
Yes.
Yeah. So we need to solve. Here. Okay. So once you get p0, p1, I mean all those, you need to put it in the x of z. You put it in the form of x of z. p2, right, x of z, and then solve for ROC. We have seen earlier how to solve for ROC. I mean, we get a particular form and then we'll see where it converges. So then you get a particular type of ROC in terms of p1 and p2. Okay. So that is how it is. Solve for ROC. Now 10th question. What he's saying is consider the figure shown. Okay, he has given a figure. Okay, saying that there is 1 0 here, and then let's just make it bigger. Okay, he's saying that there are 3 poles and 1 0 here. Then how many different time domain sequences can this pole 0 plot have? So how many different time domain sequences can we have? We need to find how many different ROCs can we have. So find the number of ROCs possible Once we get number of ROCs possible, we'll have that many corresponding time domain sequences, because once you have a Z transform and ROC, the signal is unique, right? So a hint would be like something like this, and then one more circle, and one more circle. So ROC can be like inside this region or between these two regions or outside this region. So you need to find how many number of ROCs are possible, and then correspondingly you need to find the number of signals possible. Okay, now question 11 is that x of n is equal to cos omega naught n into u of n. Identify the poles and zeros, right? Identify the poles and zeros. So how do, so simple thing would be to do is e power j omega naught n plus e power minus j omega naught n by 2 into u of n. So x of n is 1 by 2 e power j omega naught power n into u of n plus e power minus j omega naught power n into u of n, right? So we get x1 of z, for this we get x2 of z. Okay, and then final x of z, you write it as p of z by q of z again, and then solve for p of z equal to 0 to get zeros of the system. This is how you go about solve. So once you expand this, you will know, you know how to solve these equations, right? You know how to find the z transform for a system like a power n u of n. That is what you apply here, and then you get the x of z. Find the zeros for that system. If you solve for q of z equal to 0, we get the poles of the system. That is it. Okay, any more doubts? Do we have any doubts? No. Okay. 1 second. So next one would be question 12. He's saying that it this is the system. Is saying that there are many such things, many such zeros, then each is like j into so j into 2 pi by 20 into 19, and so this is j into 2 pi by 20, this is j into 2 pi by 20 into 2, so that, and then this is j into 2 pi per 20, and then there is one more 0 at 0.8, and we have 21 poles at 0 equal to 1, at 0, sorry, as z equal to 0. So we have 20 zeros of unity, and then 0 at 0.8, 21 poles at z equal to 0. This is what we have. Okay, so pole 0 plot for this. So this is the pole 0 plot, and then we have h of z is equal to k times b of z by a of z. We have k equal to 1 here, so, and then we have 21 poles. So if we have h of n is equal to, so 1 by n for 0 less than n minus 1, the h of z will be, what will the h of z be? 1 by n into 1 plus z inverse z power minus 2 z power minus of n minus 1, right? So it will be 1 by n 1 minus z power minus n by 1 minus z power minus 1, which is 1 by n z power n minus 1 by z minus 1 into 1 by z power n minus 1, right? So if we have it of this form, we have, like, basically if we have a finite duration sequence of length n 0 to n minus 1, we have that many zeros and poles, and one pole at z equal to 1, and then trivial, and the rest of them are trivial poles. But for this if we have h of 0 is, so we have 20 poles, 20 zeros at whose magnitude is 1, so z power 20 minus 1, then 1 0 at 0.8, and then rest of them are zeros at z equal to 0, which is 21, right? Now, so this is what the final form is of h of z. So in the question, what are they asking in the question? He is asking that highest power of z inverse in numerator. So you need to just divide by z inverse. What will you get? 1 minus z power minus, sorry, z divide by, how do you get it? Z divide by z power minus 21 if you do it. So basically you have this in the powers of z by powers of z, right? So divide by the highest number of highest factor of z, so that entirely this will be in the powers of z inverse by, again, some powers of z inverse. And so the 12th question equals the highest power of this one and then the highest power of this one. So this is what the 12th and the 13th questions are. I mean, I should not be doing until the final step, so I stopped it here. So divide by the appropriate power of z, so that the entire powers are in z inverse. So that is how you get the value of the highest power of z inverse in numerator and the denominator, which will give you the solution. Okay, so we have covered the entire assignment, and then we have covered some portion in LCCDE. Please let me know if you have any doubts, please. Does anyone have any doubts? Hello? Is anyone there? Hello.
Sir, no doubt, sir.
Okay, okay. Yeah. So, any other conceptual doubts in Z transform or any assignment? So I have covered in this question in this lecture. So if you see summary, first I have talked about LCCDE, then I have talked about basics of Z transform, and then I have given hints in the assignment 4. So this is what I have done. So if you I mean, I'll be here for a while. Please let me know if you have any doubts. If you do not, then maybe we can end the session. Any topics that you want me to explain? Anything? Okay, then if you don't have any doubts, maybe we can end the session here. Okay, thank you. Thank you. You may leave the call. Hello, Akhil, are you there? Hello.